So in this chapter, we're going to be looking at chemical reactions. And so the first thing we need to define is, well, what exactly is a chemical reaction or a chemical change? Well, a chemical change occurs when a substance is converted into one or more new substances. At the very beginning of this year, we distinguished between chemical changes and physical changes. Chemical changes being you're actually changing the identity of the substance. And so how can we know if a chemical change has occurred? Well, there are 4 different evidences of a chemical change. The first being the formation of gas. Now, what you will see when a gas is formed are bubbles. Okay? The second one is change in color. That does not mean you take something blue, you add it to a clear substance, and it changed color by turning blue. That means you take 2 liquids, and when you combine them together, they form yellow. So a change in color is a color that comes from seemingly nothing, but clearly a chemical change. Third is the formation of a solid, which we call a precipitate. And finally, either heat is produced or heat is absorbed. So if one of these 4 things occurs, then that lets you know that a chemical change has occurred, since you can't see with your eyes a substance converting into a new substance. We have to rely on these 4 evidences of a chemical change. Now, when we're writing a chemical equation, I gave this kind of, and your book gave this kind of mundane example of taking 2 wheels, adding a frame, and it becomes a bicycle. The purpose of this is to show you what a chemical equation shows you. The reactants would be your wheels and your frame. Those are what go into the reaction. That arrow represents a chemical change occurring, and then the bicycle is your product. Now, we say that 2 wheels and a frame react to produce, that's what the arrow means, to produce 1 bicycle. All right, so when we have chemical equations, we often put the states of matter to give a little bit more information about the reactants and the products. So states of matter are pretty obvious. The first 3 are pretty obvious. Solid is represented with an S behind the element or compound. If it's a gas, it's represented with a G in parentheses. If it's a liquid, with a lowercase l. The last one is a new concept, and that's aqueous, which is AQ. If I take water, pure distilled water, and it reacts, then that water is a liquid. But if I take a compound like salt and dissolve it in water, even though that solution is a liquid, because it's a solution, because I dissolved a solid in a liquid, we refer to it as aqueous. So a lot of what you will see in this class is aqueous, because it's easier for compounds to react when they're dissolved in water than when they're just solids. And so we're going to be dissolving a lot of stuff into solution, making that state of matter aqueous. So one of the key things that you should have already learned, but we're going to review today, is balancing chemical equations. Okay? Whenever we have a chemical equation, we always need to make sure it's balanced. Now, why do we balance chemical reactions? Well, we do that in order to follow the law of conservation of matter, which states that matter cannot be created nor destroyed. So if we look at this balanced reaction right here, okay, hydrogen has a subscript of 2. That little number is called the subscript, and a coefficient of 3. So that means that there are 6 hydrogens. So if 6 hydrogens react, the law of conservation of matter tells me that 6 hydrogens have to be produced as well. So even though you're creating ammonia, NH3, if you look, the subscript 3 for hydrogen, but there's a coefficient of 2, which means you still have 6 hydrogens. There are 2 nitrogens on the reactant side, and there are also 2 nitrogens on the product side. So you're following the law of conservation of matter because you're not creating or destroying any atoms. You started with 6 hydrogens, you ended with 6 hydrogens. You started with 2 nitrogens, you end with 2 nitrogens. And we always have to make sure that we do this. So let's look at an example of balancing. All right, so the first thing I look at, I'm going to look at silver first, Ag. On my reactant side, I have 1 Ag. On my product side, I have 2 silvers, which tells me I'm going to need to put a coefficient of 2 in front of Ag. When balancing, you cannot put subscripts. You have to put coefficients, okay? So I can't put a subscript 2 behind Ag. You can't do that, okay? So now I have 2 silvers, I'm good. If we look at iodine, however, on my reactant side, because I put that 2 coefficient, I now have 2 iodines, but on my product side, I have 3. So whenever I'm in this situation in which I have 2 and 3, that tells me I'm going to need to make 6. So I'm going to get rid of this 2 and make that 6. In order to get 6 iodines on my product side, I need to put a 2 in front of iron 3 iodide in order to get 6 iodide ions, okay? Because the I has a subscript 3, but then a coefficient of 2, so you multiply to get 6, okay? So iodine right now is balanced. You've got 6 and 6 on both sides. Awesome, but that creates a problem. I now have 6 silvers on my reactant side, but 2 on my product side, which tells me I'm going to have to put a 3 coefficient in front of silver carbonate. Now, for my last step, because I recognized carbonate CO3, since I put a 3 in front of that, that means I also have 3 carbonates, 3 CO3s. If you want to break CO3 into carbon and oxygen, so 3 carbons, 9 oxygens, you can. I find it easier just to say I have 3 carbonates. If you look on your reactant side, you also have 3 carbonates because there are parentheses around carbonate and a subscript 3. So my carbonates are also balanced. Finally, for iron, I have 2 irons on my reactant side because there's a subscript 2, and there are 2 irons on my product side because there's a coefficient of 2. So I am now balanced. The last thing that we're going to learn how to do in this section is actually write chemical equations when I give you symbols. But the first thing we have to do is recognize our diatomic elements. Now, our diatomic elements are seven elements, which when they are by themselves, you cannot write them by themselves. So for example, hydrogen does not exist as just H when it's by itself, like sodium. Sodium is fine being just Na. It's stable, it's okay. Hydrogen, however, is not stable when it's by itself and instead needs to be covalently bound to another hydrogen. So hydrogen exists as H2 when it's by itself, only when it's by itself. Okay? Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, all 7 of those cannot simply exist by themselves. You can't just have O. You can't just have F. You can't just have Cl. Those are very unstable, and so in a typical reaction, you will not see those by themselves. So let's actually write the formula for a reaction. I'm told I have sodium hydroxide reacting with iron 2 chloride. So those are going to be my reactants. So I'm first going to write the chemical formula for sodium hydroxide. Well, sodium, this is an ionic compound, so I'm going to cross charges. Sodium has a +1 charge. Hydroxide has a -1 charge, so that would just be NaOH. It reacts with iron 2 chloride. Well, this tells me that iron has a 2+ charge, and chlorine, I know, has a -1 charge. So when I cross my charges, I get FeCl2. That produces, or it forms, so I need my arrow, my products, which are sodium chloride and iron 2 hydroxide. Well, sodium chloride is an ionic compound, so again, I've got to cross my charges. Sodium has a +1 charge, chlorine has a -1 charge that produces NaCl, and while iron has a 2 charge, hydroxide is -1, so when I cross my charges, again, because it's an ionic compound, I get FeOH in parentheses 2. The last thing I need to do is balance. So I look, I've got 2 hydroxides on my product side. I only have 1 hydroxide on my reactant side, so I'm going to put a 2 in front of sodium hydroxide. Now I have 2 sodiums on my reactant side, but only 1 on my product side, so I'm going to put a 2 there. Now I have 2 chlorines on my product side and 2 on my reactant side, so I'm good there. And I've got 1 iron on my reactant side and 1 iron on my product side, so I am balanced. So in this video, guys, you learned how to identify a chemical reaction. You learned about reactants and products. You learned about the states of matter of your reactants and your products. You also learned how to balance, and then finally you were able to take what you learned in chapter 6 with naming and writing the formulas for compounds and actually were able to write your own chemical equation.